overall philosophy. I invite Himank Gangwal from California, Fremont, California. Himank would talk about how he got started with us in terms of SystemVerilog parsing and linting. And he had done two things. One is called SVCK project, which is an OOP class-based lint checker for SystemVerilog, and also talk about SVALint he started contributing. And he would basically walk us through the architecture of how he went about approaching, being a remote engineer, remote intern sitting somewhere across the Atlantic, still working with us to make some new rules. Of course, the rule specification comes from very senior people, both in the Bay Area as well as in India and UK and the rest of Europe. But then he sits there and then starts developing, and it's all happening on the open source. Himank, floor is yours. Good luck.
Okay, yeah, thank you. Let me just share my screen. Can you see? I think you should be able to. Yes. Okay. Yeah. So now we're moving on, and first of all, I'm Himank. I'm going to be a 12th grader at Mission San Jose High School, which is based in the Bay Area in California. And for my presentation, at least, I'm going to actually have a deep dive into what Verible is and how I've used it for both SVALint and for SVCK. So this is the outline. I'm gonna first go through just the introduction, and then I'll go through like the basic linting tool flow, so just the basic framework for that. I will then go through how Verible uses parsing and how I'm using it, and then I'll move on to the specific SVALint architecture, so how it's using Verible, and then how I'm using it to develop all these rules. And then finally, I'm going to go through specific examples from SVALint and SVCK, which I've actually implemented. So I think this introduction has already been covered from the last two presentations, so I'll just skim through this. This is just benefits for open source extensible linting, and then on the right, these are just all the linters, like all the different uses of linters, and obviously for SVALint, we are focusing on assertions. So over here, this is just a simplified linting tool flow. So initially we have our SystemVerilog file, and then after putting it through Alexa, we're going to get the lexical representation with all of the tokens. And then once we put it through a parser, we're going to get a syntax tree which will also have nodes, tags, and tokens for keywords. So using the selected rules that we've developed, we can combine it with with the syntax tree, and the linting tool will then print out all the violations with the specific context, which is like exactly where it is and what the actual violation is. So this is my specific approach to the basic framework I showed in the last slide. So the main difference is that we are using Verilog syntax for the lexer and the parser, and then our syntax tree is in JSON. So then the rules that I develop is also in Python. So combining the JSON syntax tree and the selected rules in which were coded in Python, the linting tool can then print out the rule violations. And the rationale for this approach is that one can replace the lexer and the parser with some other tools while reusing the lint code. And essentially what this means is that the selected rules only needs a JSON syntax tree for it to work. So this Verilog syntax, in theory, you could actually just use another parser tool, and as long as the output is a JSON syntax tree, that means this will work. So over here, I have like a specific lexer and parser example. So on the left-hand side, the code, this is just a simple module. And then the lexer will take this module, and then for each word and keyword, it will have its own token. So as you can see, the module, it gets converted to module, and then the @ is just the bit output, and then as you can see here, there's also input A, and then that's represented by the symbol identifier. And then the parser will take this lexer and then create it into like a node tree. So as you can see, the module gets created into a node with the tag of module declaration, and then the symbol identifier for foo, that will get converted into just a leaf. So in the last slide, this is just a basic parser tree. This is a generic one, but the ones that we're using, as I've stated before, is actually a JSON parsing, a JSON tree. So this is the like a specific example of like the JSON tree. So as you can see here, the tag module is and the tag module is from the module, and then symbol identifier is representing foo. And then as you can see, there's just more tags, the input for the input, and then the symbol identifiers for that letter A. Okay, so now I will move on to the SVALint architecture. So software architecture of SVALint is just using the JSON input, and then the AnyTree library. And each rule is just a few lines of code, and that is thanks to the simplicity of the SVALint architecture. So once we have our JSON tree as like the output, that is now our new input, and this has a bunch of tags and tokens. And using the selected rules, we will import in AnyTree. And the thing with AnyTree is a library which lets us search and then walk the JSON tree, and it lets us give access to all the tags and stuff, which will in turn give us access to basically the code. So using AnyTree and then using the tags, we can implement rules using depth, the tags as I've stated, and specific tokens. And combining that with the selected rules, we will then get the rule violations that that you can print out. So now that I've presented you all of this, I think I'll give you specific rule examples which I myself have actually implemented just to show like how this actually works. So over here, I think this is something which I implemented very recently. And the issue here was we wanted to detect if an assertion didn't have have a underscore as the prefix name. So the red here, this is the non-compliant code. As you can see here, CNT underscore LMT, that doesn't have a underscore as a prefix. And then the compliant code at the bottom, that has a underscore as a prefix. So if I were to run this through our linter, what we're gonna get is, I think the key main errors is actually circled. The assert start with a, that is just the rule ID that will print out, saying that this is the exact violation. Then there's gonna be just some text over here, just specifying what actually happened and what you should do. And then on the right of the tool input, there's, as you can see, there's info 12, which was the amount of rules that were ran, and then the amount of rules that caught an error. So error equals 1. And then once again, it specifies the exact ID which produced the error. And then for the compliant code, since there is no error, as you can see here, there's going to be zero errors, and this is how it would look like. So this over here is the exact rule code which I implemented myself, and I'll just highlight a few key things. So this is the assert prefix checker, and this is the rule ID. This rule ID, assert start with a, this is how it's defined, and this is what is printed out with like the circles. Essentially what we are doing is we iterate through every single node with the tag assertion items such that we look through every single assertion item. And then what we do is, using this get header name, we get the exact text for the name of the assertion. And all we're doing is, it's very simple string manipulation. We're just checking if the first two letters of the name of the assertion is a underscore. And if it's not, then it will print out the message. So what I showed previously was just an example of SVALint. Now I wanted to also just showcase an example of SVCK, which I've also worked on. So The rule example here is class inside a package. Essentially, we wanted to detect if if the class isn't defined inside of a package, and that's the error. So the non-compliant code here, as you can see, there is no package. And then in the compliant code at the bottom, there is a package. So if we were to run this, what we're gonna get is just the violation over here, which is in red. Rule 115 found class C3 without a package. So this is the context I was talking about. It specifically tells you what package doesn't have what class doesn't have a package, and then also shows you the exact block of code. And then at the bottom it has an error of 1. And then for the compliant code, obviously, since there is no error, it will not produce anything. So. And then finally, this is the SVCK rule code example. So this is, once again, something that I've implemented. There's a similar approach to the assertion one and this one, where we iterate through all of the tags with the class declaration, and then what we do is we just start manipulating all of those classes by accessing the name, and then we just do a bunch of things on that. So we get the class name, and then all we do is we're just checking if the tag k package item list is not in the parent tag. So for each class name, we're just checking if the parent has that tag, and if it doesn't, that means the package doesn't exist, because if it were to exist, that means the parent tag would have that tag. So as I said, if that's the case, then the error message is printed out. So that's the whole gist of this. So as a summary, open source linters basically allow you to add your own rule, as I've showed you before. I showed you just now. There's 2 examples. I deep dived through SVALint flow and step by step how it actually works. And then, as I've said, I showed examples with ease of implementing new rules. I believe that is it. Thank you for listening.
Thank you. Thanks, Himank.